really what we're going to do now is we're going to start getting into the first law for a closed system and dive pretty much deeper into it than we did a long time ago. Before we need to do that, we need to talk about compression and expansion work, which is kind of what you did on the test. All right, we're going to talk about internal energy, the equations for that, and enthalpy, and talk about specific heat constants, and then finally get back into the first law that we talked about like week 1 or 2. So let's talk about our first objective. And let's look at a piston cylinder device. Oh, and it can be anything. Let's just make it like this. Oh, that's bad drawing. There. Oh, they updated this. Huh. They must have just updated it from here to fluids, because that was not like that in fluids. So if we take that dotted boundary, and this is a closed system, and there's gas in here, right? And this gas has a pressure, right? How do we find the force exerted if we know the pressure? We've done this numerous times, but had people redo the homework problems because they forgot to do Newton's second law for the force balance on it. But if we know the pressure, how do we find the force that this gas maybe is pushing against this by area? Yep. Okay. Now, that's the force. How do we find the work done? What's the basic definition of work? Yep. Or it's the integral of f dx, right? Because the force could change as a function of x. All right? Okay?
Yeah.
I just told you that the force was P times A times dx. You guys okay back there?
Yeah.
Okay. So P times A times dx. What is A times dx? What's the unit of area?
Volume.
Volume, yeah, that's what I was going for, yep. So this can be written as integration of P dV. Okay? So area times dx is really, you can kind of write that as a dV. This was on your test, right? Okay? The integral, if you know your pressure and your volume, you could figure that out. The amount of work done by compression or expansion now. Okay? So this is now a new definition of work. Remember, what are the other types of work? Let's write those down that we had in the first law a long time ago. This is called boundary work, which we call WB. Okay, why? Oh, sorry, yeah, electric, yep. And what was that equation? This is work and power, they're kind of similar, right? So we can do kind of a both. What is the electric? That was volts times current, right? What other work do we have? We have fluid work. That's. We'll get to that in a minute. Yeah. Yeah. What are the other ones that we kind of used? Shaft. Yeah, the spinning shaft. Yep. We had that on your first test, right? 2 pi n dot times t. Remember that one? The gears. So we added just a new equation, boundary work now. Piston cylinder devices, they're all over the place, right? Vehicles use them, and it's used a lot to measure efficiencies later on when we start doing cycles, okay? So again, this boundary work we'll label WB is integration of P dV. This would be units of like joules. If I did little b, this would be like a joule per kilogram. Okay? And the little v is specific volume. Why do we do that? Well, your appendices have specific volumes, and you can find specific work. So this is specific work. All right. So let's get into a couple things. We're going to dive more into the boundary work. So different boundary work equations. So first case, pressure is constant. So we have WB integration of PdV I think your first question on your homework has you calculate boundary, okay? But we know in a piston cylinder device, we can have a whole bunch of different processes, right? If P is constant, what's that called? Isobaric. So this is an isobaric process. It's exactly what was on your test, right? What happens to the P of the integral? Just comes out, right? And it's constant, so technically this is just P times the change in volume. Give me the second case on your test you just handed in. What was that process from 2 to 3? Isometric. So the change in volume is 0. So what's your work? 0. Okay. What does that mean for the type of fluid? What is the fluid? What does that mean for the fluid?
There's no work.
There's no work, and it can be considered incompressible. Okay, that's where I was going with. The chain doesn't change, it doesn't compress or anything. Okay, so we have isobaric, isometric. You could do isothermal, but that one is kind of, we'll get to that later. The other process that we kind of briefly talked about was polytropic. So this states that P times V raised to the N is a constant. This is more in a sense of kind of what really happens in real life, okay? So pressure goes up or down, the volume is going to change, typically, all right? And this N is called the polytropic exponent. So this polytropic is like the next case to help you identify, okay, is it where it's not perfect, and we have perfect ideal cases, we have real life, we're kind of in the middle, okay, with these cases. Now here you have kind of 3A, if n equals 1, that states that PV at state 1 equals P2V2. Or really, PV equals a constant. All right. So if we go from one state to the next state, P times V have to equal each other because n equals 1. It's a constant. That number is always going to be the same if we go from one state to the second state to the third state and so forth. So if we want to figure out our work, what does P equal if we use this equation here? C over V. Yep. So this becomes C over V times dV and what's the integral? Well, C is a constant, right? So that can come out of the integral. What's the integral of dV over V? Remember that? What was it? ln, yeah, yep. So this actually becomes, and I'll just give you it, C ln of V, and you're subtracting the 2, and it just becomes a division for shortcut. Okay. So 1 over V, integrate that, becomes ln of V, but you're evaluating it from V2 to V1, and that is ln of V2 minus ln of V1. The shortcut is just a division, okay? What did I tell you what C was? It was just P times V. Yep. It was a constant, yep. And you just plug it back in. So key words in the problem are going to be piston cylinder device, polytropic, and if you find that your exponent is 1, you can just go ahead and use this equation. Okay, you don't have to show this work. Okay, just know that it's polytropic, it's boundary work. That's our equation right there to find the boundary work. Okay, yes?
Which V is that?
So this could be 1, 1 or 2, 2. Doesn't matter. They have to be, the subscripts have to be the same. Yep. Okay, because that is the same number. Yes?
Oh, you know, I was wrong.
This just, it'll tell you in the problem, or the homework problem I think is going to have you find it and then figure out, I have 2 more cases that I want to show you, okay? Questions? Good questions. All right. What are we on? 3b. N is 0. So you could have n equals 0, n equals 1, or n equals greater than 1. Those are our cases, okay? So if I do PV to the 0 equals a constant, what does that make it?
1.
P. Yeah, it's 1. P equals a constant. Did we do that one already?
Yeah.
Yeah, it's isobaric. We already know that equation. So that was the easy case. Typically, they're not going to be that bad. Okay? But I just wanted to remind you. All right. And then 3c. So n can't equal 1 or n equals 0. So anything else other than those 2, you get PV1 to the n equals P2V2 to the n. And this one gets a little tricky, but I'll just give you the boundary work equation. And you could try this on yourself and at home if you want. Yep, yep. So if you find that it's polytropic and they give you an n of 2.2, you can then figure out what your boundary work is. Yep. And if you notice, the first exam or second, I kind of told you, or the practice problems, I said, okay, the boundary work or the work is equal to a number. Now, I'm not going to do that. I want to say the pressures at these 2 states, or the volume is this at this state. And you can go find the boundary work, okay? And if you've been noticing, like, the boundary work is integration of P dV. That's the basic definition, right? That's calculus. But then we plug these values back in, and we do the integral, and we get this equation. Okay, that's how standard evaluations or equations work, from fluids, thermo, to dynamics, any other courses you take. Hopefully that clicks that you start with this basic fundamental equation to get down to these. But for you, for right now, as long as you identify that it's polytropic, you give your n value, you can just go ahead and write boundary work and then give me that equation, okay? Well, the last case, I guess, is 4. If I tell you that P equals A plus B, V plus CV squared, what do you need to do to find the boundary work? You just plug it in, right? And integrate. So there's going to be times where there's some process that the pressure changes based on the volume with some relationship that's not isobaric, isometric, or polytropic. It's some other weird combination you just have to integrate. Okay? Typically that doesn't happen very often. It's some weird cases. Maybe experiments, if you do experiments and they're not polytropic, but they're more like real life, you'll have to fit a line and do something like that, okay? Remember the kind of what we did with the very first homework to find the fit for the mass with the elevation versus density, okay? All right, questions on this? This covers objectives 1. So now we add boundary work. We already knew there's electric work and shaft work, okay? Now let's talk about internal energy and enthalpy. Okay. Let's do internal energy. Oops. And for you right now, we're only going to use these equations I'm going to show you for a gas or a vapor. Okay? Do not use these equations for a mixture. It doesn't work. Okay? You can use these for a liquid, but just for right now, let's just wait for that. Only worry about, okay, it's a gas. So I'm just going to give you the equation and we'll just kind of talk about it. They did experiments and they found that the change in internal energy, which we called U, remember that in the first law a long time ago, is a function of this constant. So this is just a constant, and the change in temperature. Okay, they've done many studies, and this is actually true. It works. Okay, really what they did is they did experiments, they fitted a line, and they found that, it's like a linear relationship. Okay, so this is a constant. That constant depends on the gas. So if it's hydrogen, oxygen, refrigerant, okay, air, they all have their separate CV constant. Okay, that's a specific heat. All right, and as long as you know your temperature change, okay, you can then find your change in internal energy. Where do we use that equation? Well, we end up using that in the first law if you're dealing with a gas. You can then figure out, you can plug that right in and do a whole bunch of calculations that you couldn't do before. Okay, and again, just think about it. They did experiments. They found that this was a linear relationship between internal energy change and temperature. Okay, how do I find big U? If I know little delta U, mass. Yep. So just to give you a refresher, that's how we did that before. These constants are in the back of your book. Okay? And they're right in table A1, I'm pretty sure. A1 or A2, one of those two, you'll find those. Okay? Let's see, a couple other things to remind you about. Do I want to do that now? Yeah, I can do that now. No, I'll wait. Enthalpy. is it? And it's only for a gas, this equation. Very similar to internal energy. I'll make sure I give you that right. Yep. But we use a different constant. It's called CP. Okay, so the change in enthalpy of a process from 1 to 2 is a constant, which is CP times your change in temperature. Do you remember the basic definition of enthalpy? What was it a combination of? What, two things? Internal energy and flow work. Remember that? You could also write that as P over rho. So if you, it kind of makes sense that the change in enthalpy of a system for a gas is a constant, but it has to be a new constant because H is dependent on internal energy and another function. Okay? So these two equations are very, very important. Where is the other one? I'm going to get both of them. When you start dealing with the first law for gases, okay? Heat transfer students, you've done this. Okay, so if you take heat transfer, you would actually use this in the heat transfer equations to get equations. All right. So those two are very, very important. Only use them for a gas. Do not use them for a mixture. Okay, you can use them for a liquid. It's the same equation, but the CV and the CP are different. Okay, that's all. Let's see here. Other things you've seen before are, remember your gas constant? That is CP minus CV, just for reference. And K, your specific heat ratios, is CP over CV. So just as reference, like your gas constant is those, your specific heat ratios, just to kind of give you an idea. All right, down with objective 2, questions. Where are you going to only use those two I boxed?
Yes.
Gas. Let's do energy balance, the first law, or for a closed system, which you've done 100 times already, but it's good review. Plus now we're going to do a whole bunch more with it. All right. We have an equal sign. What goes on the left side of the equal sign? Okay, we're doing energy balance, not Newton's second law, but you would be correct if we did Newton's second law. Okay, change in internal, right? Because on the left side of the equal sign is the system change in energies. Okay?
You're talking about the first law, right?
First law, yeah, this is the first law.
So like the potential and kinetic.
Yeah, okay, yes, okay.
So delta KE and delta E.
Yep.
And then it's Q plus 4.
And then over here, can I just do Q net plus W net plus E net? But we're not going to put that in there because we now know that that's only for an open system. Typically, for our systems, like a piston cylinder device, does that whole device that we're doing, is that moving up and down to the right? No. So we usually can cancel those. So we have delta U equals Q in minus Q out. Did I do in minus out? I'm going to double check. Or was it out minus in? Is it out minus in? It probably is. Intermediate though, it's switched, right? For intermediate students. No, this is in minus out. Yep, in minus out. Fluids is different, yep. So this is one form, right? What are all the units on this one? Joules. If I put dots, joule per time. Dots are rate. If I do little u's and little q's, That's the kilojoules. And they're all fine. You can still do these. Yep. So you got joules, joule per second, joule per kilogram. Oh, sure, we could add dots to these, right? Exactly. Yep. They're all the same. As long as every part of this has the same unit, you're fine. Okay? I'm just going to erase that one because you don't really see that one too often. Okay? Look, work. What are the work terms? Boundary work, electric work, shaft work, and there's other works, but for right now, I'm not going to cover it. Okay? There's other forms of work that, as long as you understand, you put them in there, you can do it, you can do that. Okay? But it's chemical and stuff that we're not going to deal with. What did I tell you about heat, really, for this class? We're either I'm going to give you the value, or you're going to have to solve for it, okay? But in the back of your mind, how many modes of heat transfer are there? Anybody remember a long time ago? There's 3. Conduction, convection, and radiation, okay? So just to give you an idea, conduction is if you have to be touching something. Convection has to do with fluids moving over an object. And then radiation has to deal with completely different type of heat transfer than conduction and convection, but it's radiation through the earth, okay, through the atmosphere. Okay. Then delta U, that is m times the little u. For a gas, what did I say it was? M times little u, but that could be CV times delta T. I kind of wrote that weird. Let me just fix that for you. Let me just give you, I'll say gas, and I'll put CV delta T. If it wasn't a gas, you went from a vapor to a mixture, how do you find your delta U? From the tables, okay? Only way to do this correctly is if you go from a vapor to a mixture to a liquid to back to a mixture or whatever, you have to go find those experimental values in the tables, okay? And figure out what exactly your change in volume or change in internal energy is.